In the early years of the Cold War, Western Europe faced a problem that could not be solved by divisions, aircraft, or nuclear warheads alone, because modern war required fuel in quantities so vast that without a secure and continuous supply, the entire defensive structure of NATO would collapse within days. And by 1949, planners in Washington, London, and Paris understood that if the Soviet Union launched a rapid armored offensive across the inner German border, the outcome would depend not only on troop strength, but on whether aviation gasoline, diesel, and jet fuel could reach air bases and depots faster than they could be destroyed, a reality shaped by the experience of the Second World War when Allied operations in France had been constrained by fuel logistics despite overwhelming industrial superiority. And as the North Atlantic Treaty Organization began formal military integration after its founding in 1949, the vulnerability of road and rail transport to sabotage, congestion, and air attack became a central concern in strategic planning, especially as the Korean War erupted in 1950 and heightened fears that Moscow might exploit Western distraction to test NATO's resolve in Europe, prompting the establishment of an integrated military command under Supreme Allied Commander Europe in 1951 and accelerating rearmament programs across the continent. Yet rearmament alone did not solve the logistical dilemma because European refineries were unevenly distributed, inland depots were exposed, and tanker truck fleets were insufficient for sustained high-tempo operations, leading NATO's infrastructure planners to examine whether a buried pipeline network could provide a protected, high-volume system for transporting refined petroleum products directly from ports and refineries to forward air bases and storage facilities. And by the early 1950s, studies conducted under the NATO infrastructure program identified that aviation fuel demand for projected wartime operations would exceed several million tons annually, with the United States Air Force and Royal Air Force requiring rapid distribution to dispersed bases designed to survive initial Soviet strikes, which meant that fuel had to be prepositioned in hardened storage sites while maintaining continuous replenishment capacity, and thus the concept of a centralized yet multinational pipeline network began to take institutional form, drawing lessons from Britain's wartime government pipelines and storage system, and from American experience with the inland waterways and pipeline systems built during the Second World War. But scaling it to a multinational alliance posed unprecedented political and engineering challenges, because sovereign states would need to permit foreign-funded infrastructure to cross their territory, standardize technical specifications, and coordinate funding under a shared command structure, all while managing public sensitivity about military installations during a period when memories of occupation and war remained vivid. And yet the strategic logic prevailed as NATO's military committee and infrastructure boards formalized requirements for what would become the NATO Central Pipeline System, a network ultimately spanning thousands of kilometers and linking ports in the North Sea and Atlantic to inland depots across France, Belgium, the Netherlands, Luxembourg, Germany, Italy, and beyond. Constructed in phases beginning in the mid-1950s under cost-sharing arrangements in which the United States financed a substantial portion through the NATO Security Investment Program, reflecting Washington's assessment that logistical resilience was as critical as nuclear deterrence, and as detailed engineering surveys progressed, planners calculated flow rates necessary to sustain continuous jet operations for tactical air forces assigned to defend the central region, with pipeline diameters and pump station intervals designed to move tens of thousands of barrels per day through buried steel conduits protected against weather and partially shielded from aerial reconnaissance, while storage depots were hardened and dispersed to reduce the risk that a single strike could cripple the supply chain. And this infrastructure evolved in parallel with NATO's strategic doctrine particularly the shift from early massive retaliation concepts toward more flexible response thinking in the late 1950s and early 1960s, because flexible response required credible conventional capability, which in turn required reliable fuel logistics capable of sustaining prolonged non-nuclear operations. And throughout the 1950s, construction crews excavated corridors across rural farmland and industrial zones, installing pump stations equipped with redundancy systems and control mechanisms, allowing operators to isolate damaged sections in the event of rupture or sabotage. While coordination bodies such as the Central Europe Pipeline Management Organization were gradually established to oversee cross-border administration, tariff structures for peacetime commercial usage where applicable, and security protocols designed in consultation with national intelligence services concerned about espionage and covert disruption. And by the time the Berlin crisis intensified in 1958, and again during the construction of the Berlin Wall in 1961, significant portions of the pipeline network were already operational, providing assurance that NATO's tactical air forces could sustain sorties even if rail lines were interdicted. And this assurance was not theoretical, because intelligence assessments of Warsaw Pact doctrine emphasized rapid armored thrusts supported by deep operations, which would attempt to paralyze Western air power in the opening days of conflict, making the survivability of fuel supply a decisive factor in whether NATO aircraft could mount continuous defensive and interdiction missions. And as additional segments were completed through the early 1960s, the system expanded into distinct subsystems, including the Central Europe Pipeline System, serving Germany, Belgium, France, and the Netherlands, and the Northern Europe Pipeline System, serving Denmark and northern Germany, each interconnected yet administratively tailored to regional requirements. And these subsystems collectively integrated maritime terminals capable of receiving large tanker shipments with inland pumping grids calibrated to maintain pressure and flow despite elevation changes across varied terrain, while operational testing verified throughput capacity under simulated surge conditions, and NATO planners measured storage endurance in days of combat operations, calculating how many days of sustained air sorties could be supported without new maritime deliveries, often targeting reserves sufficient for at least 30 days under high-intensity assumptions, a benchmark shaped by war planning cycles that anticipated either rapid escalation or reinforcement from North America via sea lines of communication. And as the system matured, it was incorporated into NATO's annual exercises, with coordination drills ensuring that in crisis, the transition from peacetime commercial flow to exclusive military priority could occur without delay, and security classification surrounded detailed maps and flow data, reflecting concerns that Soviet intelligence agencies such as the KGB and GRU would seek to map vulnerabilities, while counterintelligence cooperation among member states monitored construction contracts and access points, recognizing that a buried pipeline, though less visible than rail yards or highways, remained susceptible to sabotage if access was not tightly controlled. And by the mid-1960s, the NATO Central Pipeline System had become one of the largest integrated military fuel distribution networks in the world, extending over several thousand kilometers with hundreds of pumping installations and storage sites, moving refined products, including JP4 jet fuel and diesel at sustained industrial scale. And its existence transformed NATO's operational planning, because air commanders could assume continuous replenishment from coastal refineries in the United Kingdom and continental Europe through inland arteries protected by both depth and redundancy, thereby reducing dependence on vulnerable truck convoys and rail shipments that would likely be targeted in the opening phase of war. And this transformation was embedded within NATO's broader infrastructure modernization efforts, which also included hardened aircraft shelters, improved communications networks, and integrated air defense systems such as the NATO air defense ground environment, collectively forming a layered defensive architecture in which fuel pipelines constituted the circulatory system sustaining the alliance's combat power. And although largely invisible to the public, the system represented a tangible manifestation of collective defense, funded collectively, operated jointly, and designed explicitly to withstand the pressures of a continental conflict whose scale planners measured in divisions, sorties, and millions of barrels of fuel, setting the stage for further expansion and doctrinal integration as the Cold War entered its most structurally complex phase. As the 1960s progressed and NATO's strategic posture shifted from reliance on early nuclear escalation toward the doctrine of flexible response formally adopted in 1967, the operational demands placed upon the NATO Central Pipeline System intensified because flexible response required the credible ability to sustain prolonged conventional operations before any consideration of nuclear release, and sustaining conventional operations across Central Europe meant ensuring that tactical air forces, ground-based air defense units, and mechanized formations could draw upon uninterrupted streams of aviation fuel and diesel even under conditions of heavy interdiction and infrastructure damage, prompting NATO planners to refine both the technical architecture and administrative governance of the pipeline network, expanding pumping capacity, increasing storage depth, and formalizing multinational management bodies such as the Central Europe Pipeline Management Organization and the Northern Europe Pipeline Management Organization, each composed of representatives from participating member states and responsible for coordinating maintenance schedules, investment upgrades, cost-sharing formulas, and wartime priority protocols. And during this period, the system's physical footprint expanded to encompass more than 10,000 kilometers of pipeline across multiple subsystems, linking major seaports such as Rotterdam, Antwerp, and Le Havre, to inland depots near key airbases in West Germany and Belgium, with branch lines extending toward Italy and Denmark. While pump stations were engineered with redundant electric and diesel-powered drives to ensure continued operation in the event of grid failure, and control centers employed supervisory mechanisms capable of regulating flow rates and isolating sections if pressure anomalies indicated leakage or rupture, a feature designed to limit damage from potential sabotage or bombing. And these engineering considerations were not abstract because NATO's intelligence assessments of Warsaw Pact operational doctrine, particularly the Soviet concept of deep operations, anticipated coordinated missile strikes and special forces activity targeting rear area logistics within the first 72 hours of war, making survivability and rapid repair central planning assumptions, and accordingly, NATO integrated pipeline defense into broader security frameworks, including physical patrols, restricted access zones, and classified routing information, while also incorporating rapid repair teams trained to replace damaged segments under crisis conditions. And by the early 1970s, the system had matured into a dual-use structure in several member states, carrying commercial petroleum products during peacetime under regulated agreements that offset maintenance costs, yet retaining the capacity for immediate reallocation to exclusive military use upon activation of crisis procedures, a flexibility that required detailed contractual arrangements and pre-established authority hierarchies, so that in wartime, commercial flows could be curtailed without legal ambiguity. And during annual NATO exercises such as Reforger, which tested the rapid reinforcement of Europe by U.S. forces flown across the Atlantic, the pipeline network's ability to absorb surge demand was repeatedly evaluated, with planners calculating expected sortie generation rates for tactical aircraft, including the F-4 Phantom, and later the F-16 Fighting Falcon, estimating daily fuel consumption in thousands of barrels per air wing and ensuring that inland storage depots maintain stockpiles sufficient for at least several weeks of sustained high-intensity operations, often measured in terms of days of supply under maximum sortie assumptions. And these calculations were integrated with broader logistics planning that included ammunition stockpiles and spare parts distribution, reinforcing the understanding that fuel availability was a limiting factor on operational tempo. And during the détente era of the 1970s, while political tensions fluctuated, NATO did not reduce investment in the pipeline system, instead focusing on modernization projects that replaced aging steel segments, upgraded corrosion protection systems, and improved telemetry for monitoring flow and pressure. Recognizing that infrastructure endurance across decades required systematic maintenance, and the 1973 oil crisis further underscored the strategic importance of energy security, as sudden disruptions in global petroleum markets demonstrated the vulnerability of industrialized economies to supply shocks, prompting NATO members to coordinate more closely on energy contingency planning, including the protection of maritime supply routes that fed the pipeline terminals. And although the oil crisis was primarily economic in nature, it reinforced military awareness that in a general war scenario, sea lines of communication across the Atlantic would be contested by Soviet submarines, making efficient discharge at European ports and rapid inland distribution via pipeline critical to preventing bottlenecks. And throughout the late 1970s, as the Warsaw Pact introduced more capable aircraft and armored formations, NATO planners revisited consumption models, adjusting throughput requirements and in some cases increasing pump capacity to accommodate higher projected fuel draw rates associated with more advanced jet engines and expanded sortie expectations, while integrating the pipeline system with hardened aircraft shelters constructed under the NATO infrastructure program, ensuring that aircraft protected from air attack would nonetheless have secure refueling capability via underground lines connected directly to storage tanks on base, reducing reliance on vulnerable above-ground tanker trucks. And as computerized monitoring technology advanced into the 1980s, elements of the pipeline network incorporated improved control systems that allowed more precise regulation of pressure and remote diagnostics, though always balanced against security concerns about electronic interference or espionage. And by this stage, the NATO Central Pipeline System represented not merely a transport network, but an institutionalized logistical doctrine embedded within alliance war planning, referenced in classified operational plans that detailed phased reinforcement schedules, expected attrition rates, and daily fuel allocation priorities among competing commands, with contingency provisions for rerouting flows if particular segments were compromised. And intelligence reporting continued to inform protective measures, as NATO counterintelligence agencies assessed Soviet capabilities for sabotage and evaluated the likelihood of covert attempts to disrupt pumping stations or storage depots in the pre-conflict phase, leading to enhanced background checks for personnel and stricter coordination with national police forces. And by the early 1980s, amid renewed tensions following the Soviet deployment of SS-20 intermediate-range missiles and NATO's corresponding decision to deploy Pershing II and ground-launched cruise missiles, the pipeline system once again assumed heightened visibility within internal alliance planning, because credible conventional defense required the capacity to sustain air operations during periods of political crisis that might fall short of full-scale war, and thus readiness inspections included verification of fuel stock levels, pump functionality, and the integrity of cross-border interconnections, ensuring that the alliance could transition rapidly from peacetime posture to high readiness without encountering logistical friction. And despite its scale and strategic significance, the system remained largely invisible to the broader public, buried beneath farmland, forests, and industrial corridors, operating continuously yet quietly as millions of tons of refined petroleum products moved annually through its conduits, a hidden infrastructure binding together national territories into a single operational fuel grid. And as the Cold War entered its final decade, with technological modernization and evolving strategic doctrine shaping NATO's posture, the pipeline network stood as one of the alliance's most concrete manifestations of collective defense. An engineered assurance that in the event of crisis, the aircraft and armored units assigned to defend Western Europe would not be immobilized by fuel scarcity, but sustained by a logistical architecture designed over decades to function under the most demanding conditions imaginable. By the mid-1980s, the immobilized NATO Central Pipeline System had become fully embedded within Alliance operational planning, at a level that extended beyond engineering into doctrine, budgeting, and strategic credibility. Because the capacity to sustain air and ground operations in Central Europe was now calculated with direct reference to pipeline throughput, depot storage endurance, and the vulnerability profile of individual segments. And as NATO revised its general defense plan for the central region to account for evolving Warsaw Pact capabilities, including increased emphasis on operational maneuver groups and precision-guided munitions, logisticians were tasked with ensuring that fuel distribution would not become the constraining variable in any scenario short of catastrophic infrastructure loss, leading to further refinement of flow modeling that incorporated projected sortie rates for aircraft such as the F-15, F-16, Tornado, and Jaguar, each with distinct consumption characteristics, as well as the diesel, requirements of mechanized formations expected to maneuver extensively under flexible response doctrine, and these models were not generic but calibrated to specific theaters, taking into account the density of airbases in West Germany and the Benelux countries, the expected tempo of reinforcement flights during a reforger activation, and the capacity of North Sea and Atlantic ports to receive large crude and refined product tankers under conditions of maritime threat, with particular attention paid to discharge rates measured in barrels per hour, and the time required to move product from dockside tanks into the inland grid, because delays at the port level could cascade through the system and reduce forward availability during critical early phases of conflict. And to mitigate such risks, NATO invested in additional storage capacity near coastal terminals, increasing buffer stocks measured in days of supply so that even if maritime deliveries were temporarily interrupted, the inland network could continue to draw from accumulated reserves, while inland depots were assessed for hardening and dispersal, with some sites constructed partially underground or shielded by earth berms to reduce vulnerability to conventional air attack. And throughout this period, Alliance intelligence continued to monitor Soviet reconnaissance activity, including satellite imaging and human intelligence reporting that might indicate mapping of infrastructure corridors, prompting periodic review of classification practices and operational security procedures, as the existence of the pipeline system was publicly acknowledged. But detailed routing and capacity data were closely guarded to prevent adversaries from identifying critical choke points, and exercises increasingly incorporated simulated damage scenarios in which segments were assumed to be disrupted, requiring rerouting through parallel lines or temporary isolation, while repair teams restored functionality, demonstrating the value of network redundancy built into the original design. And by the late 1980s, with improvements in corrosion control technology and the adoption of more advanced coatings and cathodic protection systems, The alliance undertook modernization programs to extend the service life of aging sections first laid in the 1950s and 1960s, recognizing that infrastructure durability was essential to maintaining long-term deterrence credibility. And these modernization efforts were coordinated through the NATO Security Investment Program, with cost-sharing formulas reflecting national benefit and usage patterns. And while the United States had financed a substantial share of initial construction, European member states increasingly assumed greater responsibility for maintenance and upgrades, reflecting both economic growth and political commitment to collective defense. And as political transformations began to unfold in Eastern Europe after 1989, including the fall of the Berlin Wall, the pipeline network did not immediately lose relevance because alliance planners remained cautious about the pace and permanence of change, maintaining readiness standards and stockpile targets while reassessing long-term force posture. And during this transitional period, the system's dual-use aspects in certain regions continued to generate peacetime economic value through regulated commercial throughput. Yet contingency protocols for rapid conversion to exclusive military priority remained in force, and technical audits were conducted to ensure interoperability among national segments. Standardizing fuel specifications, such as NATO's single fuel policy, which favored standardized aviation fuel types to simplify logistics across multinational forces, thereby reducing complexity in storage and distribution. And as the Warsaw Pact dissolved in 1991, the strategic context that had originally driven the pipeline's construction shifted dramatically. Yet the infrastructure itself represented decades of accumulated engineering, financial investment, and institutional coordination. And rather than dismantle it, NATO member states evaluated how it could support evolving missions and force structures, including reduced but still integrated air forces, and the system's existence became part of the broader legacy of Cold War planning, in which physical infrastructure embodied strategic assumptions about high-intensity continental warfare, assumptions that had required measurable capacity in the form of thousands of kilometers of buried steel, millions of barrels of storage, and pumping stations calibrated to sustain continuous flow under stress. And although the political map of Europe was transforming, the pipeline network remained a functioning asset whose value was measured not only in peacetime efficiency, but in the deterrent assurance it had provided for decades, an assurance that any Soviet calculation about the feasibility of a rapid offensive had to account for the reality that NATO's air forces would not be grounded for lack of fuel, but sustained by a continental distribution system designed precisely to withstand the opening shock of war, thereby contributing quietly, yet decisively, to the stability of the European balance throughout the Cold War's most dangerous years. The durability of the NATO Central Pipeline System during the final phase of the Cold War cannot be understood solely through its physical scale, but through the way it reshaped operational assumptions embedded in alliance war planning from the 1950s through the late 1980s, because by the time NATO's integrated command structure had matured under Supreme Headquarters Allied Powers Europe, fuel distribution was no longer treated as a peripheral service function, but as a central determinant of sortie generation capacity, armored maneuver sustainability, and reinforcement viability, and internal planning documents consistently measured combat endurance in quantifiable terms, such as barrels per day, days of supply at maximum sortie rates, and pump station redundancy under degraded electrical conditions, demonstrating a systematic effort to ensure that logistical friction would not undermine deterrence credibility. And as the alliance refined its air-land battle-related concepts in coordination with U.S. and European doctrinal developments during the 1980s, the expectation of high-tempo air interdiction operations against second-echelon Warsaw Pact formations required sustained fuel throughput that exceeded earlier planning baselines, prompting recalibration of flow models within the Central Europe and Northern Europe subsystems, including the assessment of simultaneous peak demand from multiple tactical air wings operating from dispersed bases, each connected to underground storage tanks fed directly by the pipeline grid, thereby eliminating reliance on exposed tanker convoys during initial conflict phases. And these refinements were accompanied by detailed vulnerability analyses that categorized segments according to criticality, identifying nodes where damage would produce disproportionate operational impact, and prioritizing those nodes for additional protection, redundancy, or rapid repair capability. And NATO infrastructure committees routinely reviewed maintenance data, including corrosion rates, pressure testing results, and pump efficiency metrics to ensure that aging components did not degrade system reliability below established readiness thresholds, because deterrence depended not only on declared capability, but on verified technical integrity. And in parallel, alliance financial mechanisms under the NATO Security Investment Program continued to allocate funding for modernization projects that replaced obsolete valves, upgraded metering systems, and enhanced remote monitoring technologies, reflecting an institutional understanding that infrastructure built for a crisis that might never come still required continuous investment to remain credible. And as political reforms unfolded in Eastern Europe after 1989, alliance planners initiated comprehensive reviews of force posture that included reassessment of projected fuel demand under potential drawdown scenarios. Yet these reviews did not assume immediate elimination of conventional risk. Instead, modeling transitional contingencies in which reduced but still integrated forces would rely on existing logistical networks. And within this context, the pipeline system's measurable attributes remain significant, with total length exceeding 10,000 kilometers across multiple subsystems, annual throughput measured in millions of cubic meters of refined product, and storage capacity calibrated to sustain extended air operations without immediate resupply. Figures that had been developed in response to decades of intelligence assessments concerning Warsaw Pact mobilization timelines and offensive doctrine. And even as the Warsaw Pact dissolved in 1991, NATO documentation treated the pipeline network as a strategic asset whose utility extended beyond a single adversary, because the core principle underpinning its construction had been resilience against large-scale disruption, a principle applicable to any scenario requiring rapid fuel distribution across multinational territory, and the administrative bodies governing the system continued to function, overseeing cost allocation, technical standards, and operational procedures in a post-Warsaw Pact environment that demanded flexibility rather than abandonment. And thus the NATO Central Pipeline System emerged from the Cold War not as an obsolete relic, but as a testament to a particular mode of alliance integration in which physical infrastructure embodied collective defense commitments, translating abstract treaty obligations into steel, concrete, pump stations, and storage depots, capable of sustaining thousands of sorties and mechanized movements over prolonged periods. And, throughout the decades of tension that defined the Cold War, the existence of this hidden circulatory system beneath Europe contributed to the strategic balance by assuring that Western air power could operate continuously under conditions that planners assumed would include heavy bombardment, interdicted railways, and contested sea lanes, thereby reinforcing the credibility of NATO's conventional deterrent posture and shaping adversary calculations about the feasibility of rapid decisive victory. And in that sense, the pipeline network functioned not only as a logistical convenience, but as an integral component of the alliance's warfighting architecture, quietly sustaining readiness while remaining largely unseen. Its significance measured less in public recognition than in the confidence it provided to commanders tasked with defending Western Europe during the most structurally dangerous confrontation of the 20th century. Although the NATO Central Pipeline System had been conceived in the early 1950s as a response to immediate post-war vulnerability and the outbreak of the Korean War, its long-term strategic impact was most evident when viewed against the cumulative evolution of alliance force posture across 4 decades, because the system's existence allowed NATO planners to shift from reactive improvisation toward institutionalized logistical assurance, embedding fuel availability into every major operational calculation, from the size of tactical air wings assigned to the central region to the projected tempo of armored counteroffensives along the inter-German border. And this embedding was reflected in formal planning cycles in which Supreme Headquarters Allied Powers Europe required periodic reporting on fuel stock levels, pipeline serviceability rates, and pump station readiness, integrating these data into broader readiness assessments that also included munitions inventories and personnel strength, thereby transforming what had once been DE national responsibility into a multinational metric of collective preparedness. And during successive revisions of NATO's defense plans in the 1970s and 1980s, fuel sustainment assumptions were explicitly linked to reinforcement timelines under the reforger concept, which anticipated the rapid airlift of U.S. personnel to Europe and the drawing of prepositioned equipment from storage sites, a process that would immediately increase fuel demand as units mobilized and air operations intensified, requiring the pipeline network to absorb surges without interruption. And this surge capacity was not theoretical, but quantified in engineering specifications that defined maximum allowable throughput in cubic meters per hour, the pressure tolerances of steel segments under variable terrain conditions, and the redundancy ratios necessary to maintain flow even if specific nodes were disabled, illustrating a degree of technical precision rarely visible outside classified planning circles. And as NATO's single fuel policy matured, standardizing aviation fuel types across member air forces to simplify storage and reduce contamination risk, the pipeline system became a practical instrument of doctrinal harmonization, ensuring that multinational squadrons operating from shared bases could refuel seamlessly without complex segregation of product lines, thereby reinforcing operational integration at the tactical level. And throughout the Cold War, the network's peacetime operations provided continuous testing of valves, pumps, and metering systems, because commercial throughput in certain segments ensured that components were not dormant, but regularly exercised, reducing the risk of catastrophic failure upon activation, while maintenance crews conducted scheduled inspections, including ultrasonic testing for wall thickness, degradation, and cathodic protection calibration to counteract corrosion. Recognizing that buried infrastructure faced environmental stresses that, if neglected, could erode reliability, and in addition to physical maintenance, administrative oversight mechanisms ensured that cross-border legal frameworks permitted rapid assumption of military control in crisis, preempting bureaucratic delay that might otherwise undermine response time. And as political detente alternated with renewed tension across decades, the system's steady operation provided a form of continuity amid strategic fluctuation, anchoring alliance defense planning in a stable logistical foundation, even as debates over nuclear deployment and force reductions unfolded at the diplomatic level, and when reform movements accelerated in Eastern Europe after 1989. Alliance planners initiated comprehensive reviews not only of force numbers, but of infrastructure sustainability, assessing whether projected reductions in forward-deployed units would alter throughput requirements or storage targets. Yet, these assessments acknowledged that infrastructure once built at continental scale could not be rapidly dismantled without sacrificing flexibility, and thus the pipeline network remained operational as the Warsaw Pact, formally dissolved in 1991, marking the end of the geopolitical confrontation that had justified its creation. And in retrospect, the system's significance lay not merely in the millions of tons of fuel it transported annually, or the thousands of kilometers of steel laid beneath European soil, but in the way it translated alliance cohesion into measurable logistical resilience, shaping adversary perceptions by ensuring that NATO's air power would not be paralyzed by interdicted rail lines or congested highways, and by embedding fuel distribution into a protected, redundant, and multinational grid. The alliance effectively removed one of the most exploitable vulnerabilities of modern mechanized warfare, reinforcing deterrence through preparation rather than spectacle. And as the Cold War concluded, the NATO Central Pipeline System stood as a physical record of decades of strategic calculation, engineering coordination, and financial commitment, a hidden but indispensable structure that had fueled Europe's defense throughout the most sustained military standoff of the 20th century. As the Cold War drew to a close, internal NATO evaluations increasingly framed the Central Pipeline System not merely as a legacy asset, but as a structural enabler that had quietly underwritten every major conventional defense assumption made since the early 1950s. Because from the moment flexible response replaced exclusive reliance on early nuclear escalation, the credibility of NATO's posture depended on the alliance's ability to demonstrate that it could sustain continuous air and ground operations across the central region for weeks rather than days. And sustaining those operations required quantifiable fuel assurance embedded in hardened storage, protected transmission, and redundant pumping capacity, all of which had been methodically built into the pipeline network over decades of phased expansion and modernization. And by the late 1980s, readiness reporting formats routinely included metrics such as days of supply at projected peak sortie rates, pump station operational availability percentages, and depot reserve levels measured in thousands of cubic meters, allowing commanders to assess endurance in concrete terms rather than optimistic projections. And these measurements were incorporated into broader reinforcement modeling that calculated how quickly additional U.S.-based aircraft and support units could be integrated into European operations without overwhelming inland distribution capacity, ensuring that transatlantic reinforcement would translate into actual combat capability rather than logistical congestion at ports. And in this sense, the pipeline system functioned as the connective tissue between maritime supply routes and forward airbases, linking Atlantic tanker discharge rates to runway sortie generation through a continuous buried distribution grid that minimized exposure to interdiction. And throughout successive strategic reviews in 1988 and 1989, alliance planners examined scenarios involving phased de-escalation, partial mobilization, and full-scale conventional conflict, each time validating that the pipeline's built-in redundancy and storage depth could sustain projected operational tempo for the duration envisioned in war plans, typically calibrated around a 30-day intensive campaign window before large-scale resupply adjustments would be required. And even as political reforms accelerated in Eastern Europe and negotiations over conventional force reductions gained momentum, NATO did not dismantle this logistical backbone. Instead, conducting technical audits to determine how evolving force levels might alter throughput requirements while preserving surge capability in case political transformation proved unstable. And these audits confirmed that the network's modular structure allowed segments to be placed in lower readiness categories without compromising the integrity of the overall grid, illustrating the foresight embedded in its original design, which had emphasized flexibility alongside survivability. And as Warsaw Pact command structures dissolved and the immediate prospect of large-scale armored confrontation receded in 1991, the alliance formally acknowledged that the strategic environment had changed. Yet it also recognized that the pipeline system represented decades of multinational cooperation and capital investment that could not be replicated quickly if dismantled, and therefore retained it as part of its enduring infrastructure portfolio. Adjusting management bodies and cost allocation formulas to reflect new operational realities, while maintaining technical standards and interoperability protocols established during the Cold War. And in retrospect, the significance of the NATO Central Pipeline System lies in the way it transformed fuel from a tactical vulnerability into a strategic constant, embedding energy distribution within a continental framework designed to survive air attack, sabotage, and transportation disruption. And by doing so, it removed a critical uncertainty from alliance war planning, reinforcing deterrence not through public display, but through the quiet assurance that aircraft assigned to defend Western Europe would continue to fly as long as pilots and airframes endured, sustained by an unseen network calibrated in barrels per day, kilometers of buried steel, and pump stations engineered for uninterrupted flow. And across 4 decades of confrontation, this infrastructure operated continuously beneath Europe's surface, rarely visible yet constantly active, embodying the alliance's commitment to collective defense in material form, and ensuring that, had crisis escalated into open conflict, NATO's forces would not have been immobilized by fuel scarcity, but empowered by a logistical architecture deliberately constructed to withstand the pressures of modern war. When measured across the full arc of the Cold War, from the rearmament surge of the early 1950s to the dissolution of the Warsaw Pact in 1991, the NATO Central Pipeline System stands as one of the most technically ambitious and institutionally integrated infrastructure projects undertaken by the Alliance, because it converted the abstract requirement for sustained conventional defense into a permanently installed multinational fuel grid engineered to operate under wartime stress. And throughout its development, the system reflected a consistent strategic logic, rooted in measurable endurance rather than symbolic presence, with planners defining success not in terms of visibility, but in terms of throughput capacity, storage depth, and redundancy ratios capable of absorbing disruption without operational collapse, and from its earliest segments laid across France, Belgium, and West Germany, through later expansions and modernization programs that extended total network length beyond 10,000 kilometers, the system embodied a deliberate response to intelligence assessments that forecast rapid Warsaw Pact offensives, supported by missile strikes and airborne operations aimed at rear area logistics, and by burying pipelines, dispersing storage depots, and standardizing fuel specifications under NATO's single fuel policy. The alliance ensured that tactical aircraft across multiple national air forces could refuel seamlessly from a shared grid, eliminating fragmentation that might otherwise have complicated multinational operations during crisis, and by linking maritime terminals in the North Sea and Atlantic directly to inland airbases and depots through high-pressure steel conduits equipped with redundant pump stations. It minimized reliance on vulnerable road and rail transport that would likely have been disrupted in the opening hours of conflict. And throughout, successive decades alliance committees refined maintenance standards, corrosion control methods, telemetry systems, and rapid repair procedures to preserve reliability, while financial oversight under the NATO Security Investment Program sustained modernization even during periods of political détente, reflecting an institutional consensus that deterrence required continuous logistical credibility, and as strategic doctrine evolved from massive retaliation to flexible response, and later incorporated high-tempo air, interdiction concepts aligned with airland battle thinking, fuel sustainment models were recalibrated to match increased sortie expectations, demonstrating that the pipeline network was not static, but responsive to doctrinal change. And by the late 1980s, readiness metrics embedded within NATO reporting cycles treated fuel availability as a quantified operational variable, expressed in days of supply under maximum sortie generation and in cubic meters of storage capacity, distributed across hardened depots, providing commanders with concrete assurance that reinforcement under reforger and sustained air operations in the central region would not be constrained by energy shortfall. And when the geopolitical confrontation that had defined the Cold War receded after 1989, the system's continued operation illustrated that infrastructure built for deterrence also constituted enduring alliance capital, adaptable to new missions, while retaining the core resilience for which it had been designed. And in this sense, the NATO Central Pipeline System functioned as the circulatory system of Europe's Cold War defense, moving millions of tons of refined petroleum products annually through a protected and coordinated network that transformed fuel from a potential weakness into a strategic asset, ensuring that for 4 decades NATO's air forces and mechanized units possessed the material foundation necessary to deter large-scale aggression. And although it remained largely invisible to the public, buried beneath farmland and industrial corridors across multiple sovereign states, its steady flow represented a quiet but decisive element of the balance that defined the era, an engineered assurance that the alliance's defensive power could be sustained not just in theory, but in measurable operational reality.